Alright, so I'm going to be going over question number 6 for my video explanation problem. Before I get in any of the Matlab code or anything, I would want to go over basically my thought process of how I attack this problem. So the first thing I noticed was that since they had perfect conductance through the interface, right, and that the thermal diffusivity for the bar was the exact same for both bars, you could effectively treat these two bars, as one individual bar, right, with the summation of the two lengths. And then another thing was that because this was an explicit scheme, you could just slowly progress through that entire bar, right? And then you had to change a few of the initial conditions because of that, right? But you could treat the problem as that way. Right, so if I go to my Matlab code, if I was to run it, you would write at point 1, right, that would be the interface between the two bars, right, bar B and bar A. And then at the very end, you would reach this nice equilibrium state. So for how I'm going to explain my Matlab code, I'm going to go into a new Matlab file and just copy and paste my code and explain what I did throughout the way. So first of all, this is just some comments explaining the problem statement, right? Just reiteration of it. Nothing too special about that. This is just to help clear out the code, make things more clean when you're running it and rerunning it. This is the given alpha. I could have also put in the diameter and the thermal conductance over there, but I decided not to because it's only used in the last part of the problem, part D, so I just kept it over there. For the time increment, I just set this arbitrary maximum time of 1,000 seconds, right? That way it would have enough time to reach equilibrium. And then I gave the time step that was required of the problem of 0.1. This is the number of increments that you're taking, right? M, so you're getting 1,000 divided by 0.1. And this is your series that you're going to be doing. You run it, you go to time, you notice that it's incrementing by 0.1. And pretty much you do the same exact thing with the space direction. But the only difference now is that you're adding the two bar lengths together, like I said before. So if you run it, you go to the x direction, you notice that's increasing by the space increment, just like before. And it's going to be incrementing to the summation of the two space increments, so that's 0.15. And this is all in meters, right? So now for temperature, first I'm going to define my two temperatures. So this is going to be my temperature of bar A, and this is going to be my temperature of bar B, which will also be used for my end temperatures because they were the same thing in the problem statement. Real quickly, I'm going to initialize the temperature with the zeros function. And you're saying the size of x for the rows, right? And then the size of t for the columns. You run it, you go to temperature. This would be the x direction. If you notice, this is 31. Go over here. This is 31, right? So this is space, this is time. So this is quite a critical part of the problem. This is defining that the bar A was at initially 0 degrees Celsius and bar B was at 100 degrees Celsius, right? If I run the original, my Matlab code, that's how we're getting this looking graph, right? If I was not to run that code, it wouldn't accurately reflect the problem statement. You'd still get the same equilibrium, right? You still get the same equilibrium, but how it's incrementing through time, right? How it's progressing through time, the heat transfer is not correct, right? So I felt like it was quite critical to implement that into code in order to accurately reflect the problem. It could affect the maximum time it would take to reach that state. But anyways, that's that. Technically, you didn't really need to define T naught because it's 0 degrees Celsius, but in order to make the code more robust, right, I gave it a temperature of 0. Like let's say if I say it was 20, if I was to run it, you would notice that this would be bar length A, this is bar length B. But since bar length A was defined as 0 degrees Celsius in the problem statement, I'm going to change that back to 0. You run it. You notice that this is 0. Alrighty. And now you're just defining your boundary conditions. Right? So you're saying that the tip of bar A is always equal to 0 degrees, and the tip of bar B is always equal to 100 degrees. Alright, so this is the most important problem, or most important part of the problem. This is the actual explicit solution, right? The meat and potatoes of the problem. So for that, I would want to quickly refer back to the book. For an explicit solution, there's only one unknown variable, right? So you're just solving for that one unknown variable. And in this case, the unknown variable is ti n plus 1, right? That's the next time increment. So you solve for that explicitly. And then what you can do is you can say 2 for loops. You have a nested for loop that goes through the space increment, right? It goes through all the space increments, and then it goes through one time increment. And then it goes through all the space increments again, and then it goes through the next time increment, and so on until it goes through all the time increments. So that's that. If I run it, I go to temperature, you're seeing how the temperature is slightly changing over time, which is correct. Now you just get a nice pretty plot, nice pretty graph. And you go run it, and you get this graph, right, which would accurately reflect the problem statement. And with this graph, speaking of graph, you can find the temperature at the interface, right? So in this case, it's 66.67 degrees Celsius. Nothing special there. It's a straight line. You'd expect it to be 2/3 of the way through, so it's 2/3 of the temperature. 66.7 degrees Celsius. Now for checking the final temperature, or checking how long it would take to reach the final temperature, 1 degree less than the final temperature, you could implement a code where you're saying if, like, you can put a whole loop in this, but it wouldn't be very efficient. You can put a loop where it's saying if this is 1 degree higher than the last statement, right, then or if this is 1 degree more than what you'd expect, then you want to reduce the number of time steps, or the maximum time, and then vice versa. If it's too low, then you increase the number of time steps. But because this is a small code, you can just do this by hand, right? So for me, I found by going back and forth, just like how you can implement it into the computer, I found that it was 74 degrees Celsius, or 74 degrees seconds, or 74 seconds. You go here, you find your temperature on the graph, it's 65.7 degrees, it's slightly above 66.67 degrees. You go to 73 seconds, you run it. You now notice that it's at 65.65 degrees. So you know it's between 74 and 73 degrees, or 74 and 73 seconds. Now for part C, just checking on time. So for part C, the space increments, right? Basically, because this V, right? This V at the maximum stability is equal to 1/2, right? Or if it was over 1/2, right, it would become unstable. So you're just treating V as 1/2, and then you solve for dt. So I run it, then I go to my command window. I notice that it outputs 0.125, right? So I can check it if it's still stable by plugging it into my Matlab code. I would still run it, and you notice that it's still stable. I'm like, cool. All right. Well, if you're to slightly increase it, just by a very small amount, right? 0.001, just a very small amount, you run it, and then it's unstable, right? It doesn't work anymore. So we know that it's pretty much at the very, very maximum it could possibly be. If just like all the problem originally said, it was at 0.2. This gave me quite a bit of headache trying to figure out why it was unstable, right? I mean, I knew it had something to do with this, but I thought maybe we could use a different explicit solution. But really, because it's a simple explicit solution, right? You could narrow it down to that the delta t was too large, right? So going back to how the problem originally stated, so it's 0.1. So you get this nice graph. So for part D, because it's at equilibrium, we don't need to do fancy math, right? We need to just use a simple equation, right? The thermal conductivity times the area times the temperature difference is equal to the length, or divided by the length is equal to the wattage, right? And that's because if you run the graph, and you notice that there's no variance, so the heat flux between heat flux between the two graphs aren't radically changing, right? So you can assume that the heat flowing through the entire rod is going to be the same at the equilibrium state. So you can just use that, and at the 2/3 point, right, it's going to be the same. So if I run the code, you go to the command window, you get 2.094 times 10 to the 3 watts. All right. So hopefully that explains the problem. If you have any questions, please let me know. Hopefully that's enough to get an A. Yeah. See you on Monday, Professor.